Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to introduce the notion of a coherent sheaf in the very special case of P1. P1 being the simplest non-affine example of a variety. And this actually shows lots of interesting features already about coherent sheaves in the projective setting, and so it's a very, very good place to start. Okay, so let's look at the projective line firstly and make sure we fix how we want to think about that. As usual, we'll work over an algebraically closed field. We'll call that K here. And then what is the projective line? So it's going to be the set of ratios x to y, or points with homogeneous coordinates x to y, like that. And one way to think about that is it's the usual affine line, say with coordinates z, where z is y and x. So it'll be this usual one, but we add in this point at infinity, so z equals infinity here. Okay, so it's this a1z here. And another way to think about that is that we can also glue another affine patch. If we remove 0 from this P1 xy, you can look at the affine line that you get that's left over, and that has coordinate given by z inverse. Okay, so they're the two patches. I'll write this for the union of these two affine open subsets. Okay, so this is algebraic geometry, so of course it's important to look at the ring of regular functions on each of these. Okay, for this one here, it's just a polynomial in one ring in one variable, so that's k of z, that's quite natural. And the intelligent way to write the ring of regular functions on here is it's going to be the polynomial ring, but in the variable z inverse. Okay, so it's k of z inverse. Okay, we'll see a little bit later why this is the intelligent way to write that. Okay, so now that's how we want to think about this projective line as the union of these two affine open subsets, which are affine lines themselves. Okay, so what is a quasi-coherent sheaf M on P1? Okay, so remember, to be a sheaf means that for every open set, you need to say what the sections are, okay? So, and in particular, by the sheaf property, you only need to say what that is on all the basic open sets, okay? So if you can do it on the cover, then you have it. And remember, to give a sheaf, for example, on an affine line, okay, because you're in the affine case, you just need to give if you give a module over that, then that will give you a sheaf, okay? So the data is going to consist of something on this affine line and something on this affine line firstly. So there's a kz module on M, okay? So once you have this kz module M, that will give you a sheaf basically on the affine line where you remove z equals infinity, so the z affine line. Okay, so for every open subset of that, you can say what the sections are. You also have a kz inverse module M prime, so that's basically a sheaf on A1z inverse, where you've moved z equals 0. And then the point is that, well, you've got to make sure that the definitions of these, if you restrict to the intersection, they're going to be the same. So there's a third piece of data that you need to have a quasi-coherent sheaf M on P1. And that's going to be something which says that these two agree on the overlap. So how do you get the overlap? So the overlap is also going to be an affine variety. Basically, you're going to remove z equals 0 from here. So you invert z, so you get kz z inverse. And you remove z inverse equals 0. You remove z equals infinity. So that's z inverse equals 0. So you invert z inverse, so you have a z there. So in both cases, it's really kz z inverse. So that's the reason why we write it like that, so that the intersection is naturally given by just the this algebra here, kz z inverse. Okay, so that this is an algebra that contains both of these, and it basically is telling you how the intersection of these two affine lines, okay, sit inside each of the affine lines. So it tells you how to glue these two affine lines together. Okay, so let's have a look at that. So what do we want to do? For this M, we're going to restrict it to this intersection. So we invert Z, so you get MZ inverse. And now this is a KZZ inverse module. Similarly with this M prime, we're going to invert the Z inverse, so we'll adjoin the Z, and that will basically restrict the sheaf on here, this A1Z inverse, to the intersection, and you'll get a KZ inverse Z module, so that's also KZZ inverse module. And what you want is, you want this descent datum is just an isomorphism of KZZ inverse modules, and that will give you with these three pieces of data, you will get a quasi-coherent sheaf M on P1. Okay, so what's a coherent sheaf? Coherent sheaf occurs when these two modules are just finitely generated modules. Okay, so that's the only extra stipulation here. So let me give you a very simple example of a coherent sheaf on P1. So this is an example of a skyscraper sheaf, and we've seen the notion in a previous video of what a skyscraper sheaf is in the case of a affine variety. Okay, so here, in particular, affine line. So here we're going to look at the kz module. M is going to be a kz module is given by kz over z. Okay, so if you restrict to this affine line here, so what is that? Basically, it's going to be 0 everywhere except for, at this point, we think of it as just a single copy of k. That's how we want to imagine that, okay? So there's just a single copy of k floating over where z equals 0, okay? What's m prime going to be? Okay, m prime, that's the sheaf on the rest of it, so it's going to be 0 away from this point here. That's going to be 0 everywhere. Okay, and the last bit of data that we need to have a coherent sheaf is this descent datum. And in this case, it's fairly easy what this has to be because m prime is 0. So when you localize here, this has to be 0. So this theta has to be equal to 0. Okay, so theta is the 0 map here. And so let's just have a think about what's going on. So what's this mz inverse? Remember, when you localize this module by inverting z, what happens? Well, z becomes a unit, but z is acting by 0 as well. So when you localize, z acts both as a unit and as 0, so the localization has to be 0. So this isomorphism is from when you localize this m, this one here, by adding z inverse, this is 0, and this is 0, so it's just a 0 isomorphism. Okay, so the way you should think about this, okay, when you want to have a picture in your head, what is this coherent sheaf on P1? It's quite simple. You imagine yourself as something that kind of sits on top of this projective line. Above the point z equals 0, there's a copy of k, and elsewhere it's 0. So when you restrict to any open set which doesn't contain the z equals 0, you get 0. Okay, and that's how you get this example of a coherent sheaf. Okay, so that defines for us the notion of what this object is, a quasi-coherent or coherent sheaf on P1. So the most important thing now, of course, as is often the case in mathematics, is how do you compare objects by looking at morphisms. Okay, and what is the category of morphisms? So that's the next thing I want to tell you about right now. So what is the morphism? Okay, so we're going to get a category like of quasi-coherent sheaves and also a full subcategory of coherent sheaves. So the usual notation for that is, or common notation is co P1 or Q-co P1 for coherent and quasi-coherent respectively. Okay, so we want to look at the definition of a morphism and so that we can get this notion of a category of these quasi-coherent and coherent sheaves. So let's pick two objects, m and n. Okay, so what is m? Remember the data consists of three things. Okay, there's a kz module m, kz inverse module m prime, and descent datum theta. For n, we have a similar triple here that represents that quasi-coherent sheaf on P1. And what do we want? Okay, so basically what we want is we want a morphism from m to n, and that will consist of what? Well, basically what you want is that, well, you restrict to this affine line and you want a morphism there. So that means you want a morphism of kz modules from m to n. And then you want to restrict to this other affine line, okay? And you want a morphism there, okay? So that means that you want a morphism of kz inverse modules from m prime to n prime. And again, remember, these two things on these two patches, they're glued in a certain way via this descent datum. So you want to make sure that they agree on this overlap. And so there's a condition that you have to add to these two pieces of data, okay? And that's the fact that this following diagram commutes, okay? It's got to respect the gluing, which is this descent datum, okay? And the gluing is given by theta and rho here. So you want here a morphism from this quasi-coherent sheaf m to this quasi-coherent sheaf n, which I'm going to mark with a big capital phi here. Okay, this m essentially is given by this m prime and this descent datum. Script n is given by n prime and this descent datum. Okay, and these are morphisms of kz inverse modules. So you've got this morphism from M to N. So we can localize this homomorphism by inverting Z to get a morphism from MZ inverse to NZ inverse, and that's going to be a KZZ inverse module homomorphism. And similarly, we can localize this phi prime by inverting Z inverse, so adjoining Z, and this will give you a morphism phi prime Z from M prime Z to N prime Z, and you want this diagram to commute. And basically, this will say that these two sheaf homomorphisms on the two patches will agree on the intersection and hence on any open subset of them. And that gives you the definition of morphisms. I now want to give the very important example of coherent sheaf, which are the line bundles on P1. And they are all given by this following form, ON, where n is any integer. Okay, so let me define for you what this coherent sheaf is. So remember, we need to have three pieces of data. We need the sheaf on A1Z, so that's going to be the KZ module K of Z. Just a regular module here, okay, free rank 1. We also need the sheaf on A1Z inverse, so that's going to be KZ inverse, that KZ inverse module, the regular one. Okay, so this is, note, independent of n. Okay, and then the thing that changes and depends on n is the descent datum, theta n. So what's that going to be? So we now localize this kz at z inverse to give you kz z inverse, localize this kz inverse to z inverse to get kz z inverse, and the isomorphism of kz z inverse modules that I have, it's got to be given, of course, by multiplication by some element of this, and that element has to be a unit for this to be an isomorphism, and that unit is z to the minus n. So note that this is a unit inside here, whose inverse, of course, is z to the n, which is inside here. Okay, so that's what you have. So this example here, it's called a line bundle. So if you know about vector bundles, you should realize that a line bundle is essentially something which locally it looks like a trivial bundle where you just take the product with an affine line, and so locally they're the same. So here what we have is that even though we can vary this n locally on one of the affine lines, which is forms the open set, so an A1Z, for example, they all look the same. Similarly here on the other affine patch, they all look the same. So what's different is the way you glue these two things together. Okay, so that's similar, if you know about vector bundles, to the type of phenomena that you see there. Okay, and the way you glue vector bundles together, if you have local trivializations, is you use a transition function. So this descent datum is like a transition function in this case here. Okay, and in fact there's an exact analogy when it turns out that vector bundles do indeed kind of give coherent sheaves. Okay, so that's a whole bunch now, a whole integers worth of coherent sheaves that I've produced for you, and we're going to look at the question of finding morphisms from one of these to another one of these. So say from O of A to O of B, O of A to O of B. Okay, so what's involved there? So remember, what you need to do now is you need to have a morphism on the A1Z, so that's a KZ module homomorphism from KZ to KZ. This is in O of A, this is for O of B, and a KZ inverse morphism from K of Z inverse to K of Z inverse. And then we need for it to respect the descent datum. Okay, so let's have a look. What do phi and phi prime involve? Okay, so this is a KZ module homomorphism, so it has to be given by multiplication by some element of K of Z, because this is free of rank 1. So that means it's just given by multiplication by some polynomial in Z. So we can write down here P of Z. Similarly here, this is going to be given by multiplication by some polynomial, but some polynomial in Z inverse. So let's call that Q of Z inverse. Okay, and now let's look at the descent datum condition. O of A is given by this descent datum, Z to the minus A. O of B is given by this descent datum, where you have Z to the minus B. So these are multiplication maps. Now what we do is we look on this side here. This is about A1Z. Okay, so we have this map from given by multiplication of P of Z, and we localize by inverting Z to get you a morphism from KZ Z inverse to KZ Z inverse, and it's of course also given by multiplication by P of Z. And this one here, when you localize this map here by adjoining Z, you just multiply by QZ inverse. and you want this to commute. Okay, so that's all you have. So basically, you have a pair of polynomials, one in Z, one in Z inverse, such that this condition holds. And we want to find all such possibilities, and that will give us all the morphisms from O of A to O of B. Okay, so let's look at this condition here. So let's go around and see what this map is. Here you multiply by P of Z, and here you multiply by Z to the minus B. So at the end of the day, what you've multiplied by is P of Z times Z to the minus B. P of Z times Z to the minus B. And that's the same as multiplying by going around this way. Here you've got Z to the minus A, Q of Z inverse. So of course, if those two multiplications are the same, it means that these two elements of KZZ inverse, these two Laurent polynomials, are the same. Okay, so let's try to solve this. Okay, see how can we solve this. And the easiest way is just to put this Z to minus B over to the other side to get you P of Z is equal to Q of Z inverse times Z to the B minus A. Okay, so I've just rearranged terms here. Okay, so note that we're looking for all these P of Z's and Q of Z inverses that satisfy this equation. Okay, so let's have a look and see how can you satisfy this equation. Well, firstly, if you know Q of Z inverse or P of Z, you have the other one because they're related by this formula. So we just have to see how many Q of Z inverses, for example, solve this. Well, this is a polynomial in Z inverse, and when you multiply by this Z to the B minus A, you have to have some polynomial in Z. So that means that when you multiplied, this will involve some Z inverses most likely, okay? And when you've multiplied by this Z to the B minus A, you want to make sure that you've cleared the denominator so you get a polynomial in Z. There are no Z inverses in there. And the only way that can happen is if the degree of this, okay, is going to be at most B minus A. Okay, that's all there is to it. Okay, this Q of Z inverse can be any polynomial in Z inverse as long as the degree of it is less than or equal to B minus A, because if that's the case, when you multiply by Z to the B minus A, you'll end up getting a polynomial in Z. Okay, but once it's greater than that degree, okay, you'll have some Z inverses or higher powers of Z inverses involved, so you can't get a polynomial in Z. But otherwise, there's no restriction. Okay, and that really tells you the complete answer for the set of all homomorphisms from here to here. And in fact, it tells you really that this is a vector space of them. There's a vector space of them. Okay, so firstly, if B is less than A, okay, then this is going to be some negative power of Z. So there's no way that you're going to have this equation holding unless you've got 0 and 0 here. So hom of OA to OB is 0 if B is less than A. But when B is greater than or equal to A, what is it? It's basically just all the polynomials in Q of Z inverse are degree less than or equal to B minus A. So it's a span of 1 Z inverse all the way up to Z to the minus B minus A. And of course, if you want to think about what that is as a vector space, it's just a B minus A plus 1 dimensional vector space over K. Okay, so that's rather interesting that you can now quite easily compute the homomorphisms from one line bundle to the other. And this tells you a little bit more about them, okay? Because one thing that you might want to ask is, well, how can you tell whether these are isomorphic or not? Maybe, you know, we've come up with all these different examples, but maybe they're all isomorphic, okay? So certainly when you restrict them to each of the affine patches, okay, those affine lines A1Z and A1Z inverse, they're isomorphic. But how do you know that you've glued them in such a way to make them non-isomorphic? Well, this shows you how, okay? Because if they were isomorphic, of course, you've always got homomorphisms from one to the other, okay? But it says that if you pick different values, okay, you can arrange it so that B is less than A, and so the homomorphisms from it to, if they were isomorphic, okay, you should have non-zero homomorphisms, but the homomorphisms here are 0. So O of A is isomorphic to O of B implies that A equals B, and contrapositive, if A and B are distinct integers, then you have non-isomorphic line bundles, non-isomorphic coherent sheaves. Okay, so that's rather interesting, and it tells you that you can really compute these things in this particular instance. Okay, so the way I've set up this definition of a coherent sheaf is something that you can really compute with quite nicely, and it's often how algebraic geometers actually think about these coherent sheaves. Okay, so let me just finish up by saying lots of extra facts about this category of quasi-coherent sheaves on P1 and also the coherent sheaves on P1. So firstly, these are abelian categories, and they're also k-linear. Okay, so they're k-linear in the sense that all these Hom spaces are vector spaces over K, okay, and they are compatible with this vector space structure. And being abelian means that you can do things like, you can talk about the direct sums of coherent sheaves and quasi-coherent sheaves. If you have morphisms between them, you can talk about the kernel of the morphism, you can talk about the co-kernel of the morphism. And let me just give you a brief idea of how do you do that sort of thing, okay? So suppose you want to do any operation like, for example, a kernel, okay? A kernel, so, or a co-kernel, for example. Okay, so the co-kernel, how do you do it if you're given a morphism like this? How do you find out what is the co-kernel? Well, the co-kernel should be some sort of a quasi-coherent sheaf. In fact, in this case, it would be a coherent sheaf since you're working in the coherent category. Okay, and so you'll need a kz inverse module. So you can take the co-kernel of this phi. So that's k of z modulo p of z. Okay, and the co-kernel of this. So that's k of z inverse modulo the ideal generated by q of z inverse. So you have two co-kernels there. Okay, so you can think of those co-kernels, and then you also want to have that descent datum. So what you can do is you can look at this diagram here, and because this is commutative, you can look at the co-kernel of this map, okay, and because localization exact, that is just the localization of the co-kernel here, and you can look at the co-kernel here, okay, and because this commutes, there's an induced morphism. And since these are isomorphisms, you're going to get an isomorphism here as well, okay? And what that allows you to do, that isomorphism will be the descent datum for a co-kernel, okay? And similarly, you can just basically, because essentially the category of modules, okay, they are abelian categories, so you can do things like take direct sums, kernels, images, and co-kernels, okay? You can use them to construct the notion of kernel, co-kernel, and direct sums for these two categories as well. I hope you enjoyed this adventure in pure mathematics.